Hey everyone, so today's video is gonna be about the idea of polymers revision. So we're gonna revise the idea that there's a thing called addition polymers and a thing called condensation polymers. Addition polymers are made by unsaturated monomers. Remember, the monomers had carbon-carbon double bond on them, so those were unsaturated monomers with carbon-carbon double bond. While condensation polymers are made by the monomers that have two functional groups at least within the molecule. It could be two carboxylic acids, two hydroxyls, or two amine groups, or a mix and match. So two amine groups. For example, ethene, which is a two carbon unsaturated molecule, makes polyethene. A propene molecule could make polypropene, and another two carbon chloroethene could make chloroethene polymer. In condensation polymers, you need two functional groups on each side of the monomer, amine, carboxylic, or any mix and match of these functional groups. In the case of addition polymers, there is no byproduct. So there is no byproduct, just one long chain polymer. Because when addition reaction happens between the carbon-carbon double bond, there is nothing released out of it. But in the case of condensation polymers, small molecules like water, like HCl, are eliminated each time a reaction happens between the functional groups. So H and OH are eliminated every time. In the case of addition polymers, the backbone of the polymer is made by carbon-carbon linkage. There is no oxygen, there is no nitrogen in the central linkage of the polymer. It could be anywhere above or below the main chain. But in the case of condensation polymers, the backbone is linked by ester linkage, or you can say the amide linkage. It has to be there in the main backbone. Over here you can say that the main linkage is the carbon-carbon single bonds. You don't care about the chlorine. And in the case of condensation polymers, it's either the ester or the amide linkage. Now let's try some questions extracted from the past papers. For example, this molecule over here is a polymer. You can see extended bonds coming out from both sides of the molecule. So it's definitely a polymer. And when you look at the main backbone of the polymer, you can definitely identify that it's the amide linkage. Now it's a polymer, it's a condensation polymer. Let's try to make the monomers. It's the amide linkage we know. Now our task is to draw the monomers out of it. I'm going to break the amide linkage from the center, so the carbon and the nitrogen are separated when I break it. Now we can see what the monomer supposedly looks like. So let's redraw it. Let's draw the box, the nitrogen along with the hydrogen on the left and the carbon double bonded oxygen on the right side. Similarly, the other monomer will be drawn the same way. Draw this exactly, the shaded box, the nitrogen, hydrogen on the left, the carbon double bonded oxygen on the right. Now nitrogen gets a hydrogen to complete the amine group, and the carbon double bonded oxygen gets OH to complete the carboxylic acid group. Carboxylic acid group is on the right side now. Similarly, on the other monomer, nitrogen gets H, carbon gets the OH to complete the functional groups. We have the monomers. Let's try this one. This again seems a polymer because it again has the extended bonds coming out from both sides. Now which monomer is it? We have to notice that there's ester linkage, so it's kind of a condensation polymer because it's got ester linkage in the backbone. Now when we look about the monomers, we have got to break the ester linkage. So the carbon and the oxygen of the ester should be separated. And every time I do that, I can see what the monomer should look like. I draw this exact molecule starting from the left, so oxygen, then the CH2, and then the carbon double bonded oxygen is exactly replicated. Similarly, the other monomer is drawn same way, oxygen, CH2, carbon double bonded oxygen. To complete the monomer, I do the final touch up, which means H with the oxygen and OH with the carbon double bonded oxygen to complete the functional groups. So you get hydroxyl on the left and acidic on the right. Similarly over here again, the OH is completed by adding H and the carboxylic acid is completed by adding the OH. Now that's the complete monomer. You get two monomers which are apparently the same one. This molecule is again a polymer because it's got extended bonds and it's got carbon-carbon linkage, so it's addition polymer. Over here, we draw the monomers by copying this segment. So CH3, H on the top, H is on the bottom is exactly copied. And in order to complete the monomer, we draw a carbon-carbon double bond because the monomers, in the case of addition polymers, have got a carbon-carbon double bond. So remove the extended bonds and make the carbon-carbon double bond. Let's try this molecule. It is again a polymer because you can see the extended bonds again. Now you can notice that there's oxygen in the backbone. Definitely not a carbon-carbon backbone because it's oxygen over here. I know that it's not ester linkage. I know it's not amide linkage. It's definitely not ester because the carbon double bonded oxygen is not there. It's not amide, but it's not a carbon-carbon linkage. So you can notice that the oxygen, silicon and CH3 on the top and the bottom make the monomer. They are the repeated units over here. So let's just copy the repeated unit. Okay, yeah, from here. So every time I break it into the repeated units, I get the oxygen, silicon, there's a CH3 on top, there's a CH3 on bottom. Now in order to complete this structure, I need H and OH on both sides. So I get the H with the oxygen and OH on the other side. So remember H2O is made. So in order to reverse that process, you add H on one side of the monomer and OH on the other side of the monomer. And that's how you get a complete monomer. So H and OH are added on both sides. Let's try this molecule. This is again a polymer because you can see the extended bonds on both sides. Even though there's not a bracket over here, but you can see that it's a polymer. You notice that within the main backbone, there are ester linkages out here. So that's a condensation polymer. That's ester linkage right over here. Not amide linkage, not a carbon-carbon central linkage. So it's definitely a condensation one. In order to make the monomer, I'm gonna break the ester linkage. So I'm gonna split the carbon from the oxygen. Everywhere I see the ester linkage, I'm gonna break it, so that I can see what the monomer looks like. You can notice, starting from the left side, there's an oxygen on the monomer, there's a straight blank box, and there's another oxygen. For the other monomer, which is in the green box, you can see there's a carbon double bonded oxygen, there is another box, and there's another carbon double bonded oxygen on the right side. Now the monomers are not complete yet. You have to add H's along with the oxygen to complete the hydroxyl functional group. On both sides, you can see it's on both sides. And then with the carbon, you get the OH to complete the carboxylic acid group. If you just added the H with the carbon, that wouldn't be carboxylic acid group, so you would be making a mistake. Make sure you add the OH with the carbon double bonded oxygen. So these are two different monomers. One has 2 hydroxyl, the other one has 2 carboxylic acids. This one is again a polymer because I can see the extended bonds on both sides. So even though it's not a bracket over here, but it's a polymer. I can see the main linkage is a carbon-carbon single bond linkage. So it is a carbon-carbon backbone. It is addition polymer, not condensation one. There is no ester right here, there is no amide, so it's not condensation, it's got to be addition. When I want to make the monomers, I can split it into the pairs. So each pair of carbon determine the monomer. I'm making these brackets to make it more clear how the monomer looks like. The monomer has 2 carbons in the center, and there is a CH3 on top from both carbons and on bottom from both carbons. Now in order to complete the monomer, do add a carbon-carbon double bond because the monomers always have a carbon-carbon double bond on them. So I hope the idea that the monomers got to be unsaturated is clear, and we make the carbon-carbon double bond. It's a 6-carbon monomer with a carbon-carbon double bond in the center. So I hope the practice helped you understanding how the polymers are converted into their monomers. Stay tuned guys, in the next video we'll learn more about it. Thank you.